Hello, everyone. It's me, Aidan, the one that Sam introduced. As Sam said, definitely feel free to drop me questions in the chat, and we'll get started with tonight's presentation, the Unity shader graph, custom effects made easy-ish. um, First off, we'll skim over this "Who am I" slide because Sam mostly hit it. I got a picture of me. I work at Aesthetician Labs. Some links, some games I worked on, all good stuff. Let's get into what we're going to learn tonight. Um, for the presentation portion of this talk, I'm going to cover how computers render 3D graphics, how shaders work, the parts that make them up. And in the practical section, we'll cover the basics of using the shader graph and go over how to set up some cool effects that I've prepared that I think are a nice way to learn the very basics of shader graph creation. The first question that we should answer tonight is what are shaders for? What are we doing with these things? Well, you can use them to put fancy lighting in a video game, like this crazy lighting you see here in this screenshot of Minecraft. You can also use it for fancy effects, and often save performance over different methods of achieving these effects, because you can create the effect using the graphics card as opposed to things that have to run on the CPU. Uh, and that's all well and good, but perhaps more importantly, they're really for everything. At least everything that your computer renders as graphics on the screen, perhaps in a game engine. And this is because shaders are fundamental to the process of rendering graphics, 3D or 2D, on your screen, accelerated by the graphics card. So now just a little bit of information about how computers do that, how they show you pictures. And first, we just need to do a little bit of 3D graphics terminology. For anybody who doesn't know, on the left here, we've got a picture of just about the most basic mesh you can have, a cube. It's made up of vertices, edges, and faces. And on the right, we have a much more complicated mesh that shows off why you might call this a mesh. Because with enough complexity, it starts to look like a net of a sort. And this is how almost all 3D objects that you see in video games are represented. From that data, the graphics card can create an image. And we're mostly going to gloss over this, but I want to put this into your mind because it's helpful to know, even when using the shader graph to create shaders, the rough steps. So moving from left to right, we start with a list of vertices. And it's not really covered in this image. We also have a list of edges, which is it essentially describes how the vertices are connected. And so it goes through the vertex shader, which is a special kind of shader we'll talk a little bit more about later. And what the vertex shader does is it takes the vertexes and edges and turns them into triangles, which is the data needed for the rasterizer. And what the rasterizer does is takes that triangle data and turns it into pixels on the screen. And you can see here this from this representation, the vertices having edges added to them and being turned into triangles. And then the moment where it goes through rasterization, it becomes pixels on the screen. Um, then the fragment shader, which is another special kind of shader we'll talk about later, takes each of those pixels and assigns a specific color to it. Whether that's the red of a strawberry or the darkened area beneath it on the floor for lighting. And finally, uh, that's put onto the frame buffer and displayed on your computer monitor. This is a little bit of a text abbreviation of all that stuff I just said. The GPU, it takes vertices, it rasterizes them, and then renders those pixels to the screen. Again, especially with the Unity shader graph, you really don't need to worry about all this too much, but I wanted to provide context for the idea of a vertex shader and a pixel shader. And now we'll go through one more time because it is important to remember the difference. A vertex shader, it runs once per vertex per frame. So if you have a cube, that's likely made up of 8 vertices. And so for each frame that is rendered, the vertex shader will be run 8 times. That's not too many times. That's 8 times 60, whatever that is, times per second. Now, if you really want to do some fast computation, the pixel shader is where it's at because it is run once per pixel per frame. And so if you're rendering your game at a resolution of 1920 by 1080, like a standard monitor, at 60 FPS, the code that makes up a pixel shader has to run 124,416,000 times per second. uh, and that's a lot. So this is one place where it's a good thing the graphics card can come in to save us. And it's too many times. Well, luckily for the CPU, that would be too many times. It's too many cycles for the CPU. But graphics cards are structured around being parallelization machines. So they break up the task, and instead of having to do it consecutively 124 million times, it breaks it up and does 1,000 of those at a time, and thus can churn through that kind of work much more quickly. And with that, that's sort of the information that I felt that I needed to cover. And now we can get hands on. And in case anyone wants to download the repository for the project later, it's available at this link. It's github.com/Aidan Markham/RGD-shadergraph-talk, and I'll drop that in the chat right now if I'm allowed to, and I am. So let's take a look at the sort of the Unity project I've set up for us today, just as a little template. Um, Everything you see here is either free assets or something I put together. This little man is somebody I had sitting on my graphics card, or I'm sorry, sitting on my hard drive from another project. And it's simply the Unity third-person controller and a scene made out of some wonderful Kenny.nl assets. So we can run around in here. There's some trees. Um, some nice mountains in the background. World eventually ends when we get over here. Nothing too big, just enough room to demonstrate some of the effects we're going to be preparing. And so, diving in to take a quick look at the scene, we can see nothing too complicated here. And if I look into my project view, I can see that the project is made up of very few materials, which I've done to make it as simple as possible to modify. We've got the character material, which is possibly the most complicated. It's got a palette image. Essentially, that's controlling the colors of this character here. And then we have several other simple colored materials that are for wood or rock, leaves, ground, cloth, etc. And from these 6 materials, this whole world is built. And right now, the shader these are using is the standard universal render pipeline lit shader. And so now what we can get into is how to create a shader graph. And like so many things, it's nice and obscure deep into these Unity menus. But if you open a new Unity project with a new version of Unity, you will have access to this. And I'm just going to create a lit shader graph and call this basic. Now, double click on this to open it up. And this is what we're presented with. This is the basic functionality. And you might recognize the word vertex here. And there's also fragment here. Do you need to be working in URP to use shader graph? Not necessarily. I do believe there is a version of the Unity shader graph that works with the legacy render pipeline. I can't speak too much to that though because I have largely used it with the universal render pipeline, although I do understand that everything you see here tonight will work, should work the same for the standard render pipeline. Um, we have this vertex block up here, and this allows us, yeah, the built-in render pipeline is what I mean by the legacy render pipeline, the basic one. And I think HDRP has a version of it as well. So we have our vertex block and our fragment block, and what these represent is our two different shaders, the vertex shader and the pixel shader, or as it's often also called, the fragment shader, the language they've chosen here. And so if I save this basic shader, I can go into any of my materials. We'll do this character one here, and go into shader graphs, and we'll have our basic shader. And it is a very basic shader. As you can see, we don't even have any properties. There's no texture, no color, just default Unity gray. And so the first thing we're going to learn how to do is adding properties to these shaders. Um, and I think perhaps the most basic is maybe we'd like to have our fellow have a color. And so I click this plus here. These are all the types we can add. I've added a color property. And even saving that, just like so, we'll see if I select my shader, in the inspector we now have the color property. But if I set this color, it doesn't do anything yet, and that's because we haven't wired it up. And so all we need to do that is to drag the color property in here, and then we get a node that has this color input. And if we connect that node to the base color of the fragment shader output and save that, now we should see that we can change the color of our character. And so that's very exciting. But as you might recall, this character was he had a texture because he had his eyes and everything, and I'd really like to get that functionality back here. So let's look at how to set up a texture. So the first thing we're going to need is we're going to actually need to get the texture. We'll call that main texture, and can drag that in. And you can see here on these nodes, the color node has a 4 after the name, and that's because this is a vector 4 data. Normally, in sort of regular Unity programming, vectors are mostly used for space, but in the world of shaders, everything is a vector basically, unless it's only has one dimension, in which case then it's just a float. But this is a T2, so we can't connect that to base color, and that's because this is a texture, and we need to tell our we need to tell the graphics card what pixels of the texture to show for which pixels of this character. And luckily, as you'd expect, there's a node that does just this for us with the sample texture 2D node. And it takes two inputs. It takes a UV map and a texture, and it also takes a sampler state, but we don't need to worry about that for now. So if we simply connect that texture and then connect the color output to the fragment shader, we'll see, well, our character looks all white right now, but if we select the texture, then he looks like this. Now you may have noticed when I switched back to the standard shader, his texture is still here. Unity has saved this texture. Now, your first thought might be that, oh, it's his base map here, and we called this main texture. But that actually isn't quite it, because if we call this base map, which we can do to keep things nice and consistent, it won't sync up. It won't remember. And so it's important to recognize that with all of these properties, there's the user-facing name, and then there is the reference name, which we've been given a default one, texture 2D, and then this long string. The easiest way to see, or I should say, the texture is saved by the reference name, not the display name. So you can change the display name whenever you want, and so long as the reference name stays the same, and so long as the reference name is the same across multiple shaders, that data will be preserved. Now, if we want to find out what the reference name is, because it just says base map here, we can actually open the debug inspector, and under the saved properties, we can see all the different textures that it takes in, and see that we've got one called main text. And that's the case for almost all of the Unity default shaders, that the main texture is called main text. And so if we simply set the reference name to main text and save that, now when we switch to our basic shader, we see the texture is preserved. Now, we still have this color, but it doesn't do anything anymore because we disconnected it. And in the basic URP shader, we have this nice tint color we can use to tweak the color of our texture. And say maybe I want that behavior in my own shader. So let's look at how we can set that up. So looking here, we have our base map comes in and it goes through the sample texture 2D. And that outputs that RGBA4, that vector 4 that represents the color. And we have our color, which is an RGB4. And the way we can combine those is to multiply those two things together. So what I've done here is I've created a multiply node, which does exactly what you'd think it would do. You connect the two vector 4s into the A and B inputs, and then it outputs the two vectors multiplied together. And this works for position vectors, direction vectors, colors, all of it. So now if we come in here, we can see that we now successfully have the ability to tint this character. One more thing we can do is multiply is quite cool, but we can also use the blend node, which if you're familiar with Photoshop or GIMP or anything like that, you might remember the various layer blend modes. And what blend does is it gives us access to those. So we can copy our setup here. And if we set this to multiply, everything will work just like it did. But it also gives us access to some other interesting ones, like, for example, overlay, which has its own interesting effect where instead of it being white makes everything the same, setting it to 50% gray will make everything the same. And if we go back here, there's all sorts of options to explore. But for now, I'm going to leave it at multiply because that's the standard behavior of the Unity shaders. And it's perhaps the easiest to wrap your mind around. So with this, essentially what we have done is we have used nodes to create our very own fragment shader, um, our own method of setting the base color. The way this works within Unity is when we save this, it automatically converts these nodes into shader code, and then you run that shader. And the main advantage of this is it's both easy to understand. It's much easier to notice when or to figure out what the problem is when things aren't going right. And I personally find it's also just much faster to create things this way. And so we'll save our basic shader here, and I think we'll move on to the next effect, which I like to call inflate. And so I'm simply making a duplicate of our basic shader and opening that. So here we are. So right now we don't have anything connected to our vertex shader. And the vertex shader is perhaps one of the most fun things to play with. Um, Now, the way that it works is if nothing is connected to any of these nodes, we simply get the default behavior. But if we connect anything to them, then we get to determine the position. So if we say connect a vector 3 to the position, this will cause us problems. We also need to change this shader to be our new inflate shader. Well, and we can't see our character anymore. And this is ultimately because the vertex shader has set the position of each vertex to 0. It's not what we want. Luckily, we can use the position input. Now you can see here, next to the position node, it says object space. And this is important to notice because the position node's default space is world space. And that is the position of a vertex oriented around the whole world origin. Whereas object space is the position of each vertex oriented around the character's pivot. And so if we set this to object and connect this, we'll see that now our character looks like normal. Now, let's try tweaking this in some ways. Let's multiply it. And we'll add a float, call it inflate amount. And we'll connect that to the multiply. Another useful thing to do, because right now, inflate amount, because I just created it, its default value will be 0. And so if we save this and look, we'll get nothing again, because it's the position times 0 is going to equal 0. We're right back in the same situation. If you select any of your properties in the node settings in the graph inspector, it's also possible to set a default right underneath where you set the reference name. So I'm going to set my inflate amount to 1 by default. And now when we come in here, we'll see it's still 0 because it's saved, but if I had created a new material, it would be set to 1. So if I set this to 1, we have our character. If we drag this, we could see that the character gets bigger, scaled around the pivot. Or scaled around this point, actually. So I believe that is the pivot of the body. That's still not quite what we want. This isn't really that good of an inflate effect. We can do better. So let's talk about what an inflate effect might actually be. That simply made the character bigger, but we want him to get thicker, or I guess thinner if we set it to a negative value. And so really what we want to do, if we look at the wireframe here, is looking at, for example, the hand of the character. At this point, we can imagine an arrow, a vector, the normal vector, sticking directly out of the model. What we want is to move that vertex, rather, along that normal vector. And so we'll set it up to do just that. Luckily, there is a geometry input just for this, the normal vector. And because we're already operating in object space, we'll set the normal vector to object space also. Let's connect this to the multiply. So we'll multiply our normal vector by our inflate amount. And I'm going to change the default of this back to 0 now, because we want it by default to not do any inflation. And like we said, now we have this normal vector, an arrow pointing out at each vertex, multiplied by this inflate amount. And what we'll do is we'll add that to the position. And so if we save this and take a look, now if we increase inflate amount, ooh, that's a very sensitive value, but we can see he gets to be quite thick. Or vice versa, we can make him quite thin. Yes, I love the automated alignment guides. And the cool thing that we'll see here is the shader, it works with the animations because it's running on the graphics card. And so now we have our wide fellow, nice and puffy. And there's all kinds of things you could do with this effect. You can animate this material property. Actually, let's do a little fun side tangent just for fun. What if we had looking here at our inputs? This is under scene. Basic? Yeah, basic. We have time. Now time, this is a very powerful node. And what I'm gonna do is I'm gonna add another multiply node, and I'm gonna connect the sine time, which is basically it's quite literally the sine of time. So we'll see instead of time, which is a value that just goes up each second, sine will go up and down once per second. And we'll connect inflate amount to that, and then we'll multiply that. So now, if we go into our scene, we'll see him grow and shrink by the inflate amount. This model definitely gets interesting during the shrink period with the mouth and all. But the cool thing about this is the one way to do this would be as a like a blend shape animation, perhaps, which is would be interesting, but that would be quite expensive. Whereas this we get basically for free because all we have done is we've overridden the way that the computer renders our character. And so I'm gonna go back and I'm gonna get this time thing out of here. Send him back to just being a little fluffy, a little chunkier than he was before. And so with that, we've created the our first vertex shader. And so that's all very well and cool. We've got our character here. We can make him big and small. Can even um if we choose to set the mode of this to a slider and say negative 0.001 is the min and positive 0.001 is the max because it's all too precise. And now we get a nice slider bar here and we can control his thickness. But this effect only affects the character. I mean, and sure we could apply it to the whole world if we chose to. Um, that's all cool, but it's just not very interesting. And we actually saw there when we changed that the same way that we had to change the color property, or the same way we changed the texture property so that the texture would sync, we can do with the color as well. So I'm going to take care of that very quickly. Just like I did before, I'm going to debug. I'm looking at colors, and we can see that the one that probably is the main color is base color, because we can see it even has the color. And so if we go back into our inflate shader, we set this color to be base color as a reference name. Now, if we change, say, the leaves on trees to basic, oh, they won't keep their color. Hmm. I guess maybe I was wrong. Maybe it is just color. This is the process, people. Shaders are wily bits of code. Now we go into here and we go to basic and all right, who knows? I'm not going to get sidetracked on this any further. Never mind. No, that's the inflate shader. Oh, yes. Thank you, Patrick Code. That is the problem I'm having here. Because now if I set this to base color, and I should have done this in the base shader. That's actually would have been more to my notes. If I went a little off script. Anyway, that effect is cool, but it only affects the player character. Maybe I want a cooler shader that affects more things. And so I'm gonna copy my inflate shader and we'll make another one. And I'll call this Animal Crossing. And I'm sure, can you inflate the trees? Oh yeah, I can inflate the trees. This guy thinks I can't inflate trees. I actually don't know why. Oh, it's because it's too small. So sometimes you'll see um, that. What have I done? Oh, I turned off lighting. uh, what we're seeing here is that now when leaves are set to the inflate shader, this this has an effect. It's just really slight. Um, and this comes from the scale of the model. So this model is perhaps quite scaled down from what was created in the editor. So all we would need to do there is um, either remove that min-max node, or I believe you can also just set that value. No, you can't. So yeah, we'll remove the slider for now, and then that'll allow us to set that to 1. These tree models don't really inflate so good though, because they've been edge split. Although it is kind of interesting as an explode effect to see all of them do that. Now the video game aware of everyone will probably have some idea of where I'm going when I talk about an Animal Crossing shader. And you may understand from our little demo scene how that might look. So let's set it up. So let's take a look at what we've got here in the Animal Crossing shader. Obviously, this is the base from Inflate. So I'm going to remove our old vertex position shader. We'll save that. And so now we just have a color and a tint once again. And I'm going to delete the inflate amount property now that we don't need that anymore. And I will add a few more properties. First one being a float rotation amount. And that'll control sort of how powerful the barrel effect that we see is. And I'm going to create a vector 3. We'll call it the pivot offset, which is perhaps an overly specific name for the offset from the camera that we will apply the effect to. Because by default, with no additional work, the way that you might think to set this up will set it up oriented around the camera, the problem being that the character is actually where you want the effect to center. And so I'm once again going to create a position node with world space this time. And I'm going to create a camera node. And we can just for fun, we can take the distance here, and we can do subtract. We'll take the position, and we will multiply a vector. We have this vector here. I'm going to set it to -1 on the y, so it's essentially a straight down vector. We multiply that by the distance, and then we actually we want to add if we're doing it negative. Plus, that's easier to understand. If we add that, and then we do this, we'll get something. Let's take a look at what that looks like. And first, we'll need to set all of these shaders to our Animal Crossing shader. And what we see is kind of wacky, actually. It's if I hit play, everything will work as before, which is an important note because shaders only control the rendering of the game. They don't control actually how the game works. You can get some really wild situations like this. Now, this is not quite as nice of an approach because this also is working in every axis. So let's take a step back and think about how we really want this to work. Add that position node back in. Essentially, in an Animal Crossing style effect, looking at the world, as we get further away from the camera on the z axis, we want the world to get lower. And as we get closer to the camera, or it's sort of behind the camera. We want the world to also get lower. And so if we just do the distance between the position of a vertex and the camera's position, we end up with this crazy, there's too many axes at play. And so what we really should do is split out the channels. The split node is one of the most useful, but least glamorous. And all it lets us do is we can drop in the camera's position, and now this gives us access to all of its requisite parts. This is also quite useful in combination with a vector 3 node, because say, for example, we want a vector 3 to do math with, but we only want a single axis of the camera and the other two to just be 0. This is a really clean way to set that up. Now, we have the camera and its y position saved as a vector. Instead of doing a distance node, I'm going to use subtract. The reason I'm using subtract is because if it's a distance node, the things in front of the camera, the distance goes up. And on the other side of the camera, the distance also goes up. So we actually will see a range of values that's mirrored on the camera. And that gives us less control over what we'd like to do. But if we have subtract, we see the values become positive in this direction and then negative in this direction, which gives us more numbers to work with. It gives us more control over the situation. We have this subtraction, and we will, I'm gonna make us a little more room here. We're gonna split this out again. And we're gonna multiply that with the rotation amount. So just to keep track of what we're calculating here, now after split, this value will represent the I will happen to be available in the Discord later. Feel free to at me, and I can happily answer any shader-related questions you have. Um, if we multiply this with the rotation amount straight away, or I'm sorry, I was explaining what these values represent. So this y value now is the distance from the camera in such a way that it becomes positive in this direction and negative in this direction, or vice versa. And so if we do our multiplication like this, we'll end up with a sort of upside down V type situation, which is not actually the shape we want. We want an Animal Crossing style barrel. And the easy way to achieve that is to add a power node, which is essentially the same as raising this to the power of 2. And that'll give us that nice curve that we want to see. So now, after all of this, we have for each vertex a offset as a single float value. And we want our vertices to move on the y-axis up and down. So we'll assign that to the y of this vector 3, and we'll add that offset to our original position. This is all very cool, but if we add this directly into the into our vertex shader, we're going to have a problem, and that's because these calculations are happening in world space. And so we'll save ourselves from one of the most common gotchas with shader programming and use a transform node to convert from world space to object space, because as you might remember, this vertex shader expects an object space at the end. We connect this up. This type variable, it takes either position or direction. We are talking about positions right now, but directions, the math is slightly different if it's a directional vector as opposed to a position to make that transformation happen appropriately. And so if we save this now, we should That is, if I've connected everything correctly, see everything being the same. However, if we change this rotation amount, and I have all the shaders that make up the scene here, we see the world starts to bend and flex. And so let's set this to a really quite small negative value, negative 0.01 perhaps. And suddenly we have an Animal Crossing type effect. One little issue is that the character's feet are floating above the ground, and that is because this effect, as I had originally described, is operating around the camera space. And so I'll really quickly add that pivot offset in. And that's as simple as we have the camera's position, we have the offset. So we'll add the offset to the camera's position and connect that in. And just like that, now we can push that offset back and forth. We can put that to just a little bit away from the camera. And now if we go in here and we run around, you'll see we get this cool Animal Crossing sort of barrel world effect. And again, just like the previous one, we have simply added a few little bits of math to some work that was already happening. So this effect costs us nothing, really. It does cost us something, but it's so marginal. Uh, on top of the work the graphics card already has to do. And at this point, it's just fun to run around and see this little fellow go. And so that's quite an interesting one. What about one that maybe has some different gameplay implications? Let's return our scene to the default shader just for a while. And here we are back to the default. Now, the next one I want to create is a what I like to call a clip circle shader. Oops. And this is another fragment shader. Yes, this whole Unity project, including the shaders I've created tonight and complete example versions of the shaders that are maybe a little bit better organized, are available at this link. And I'll paste this in the chat one more time. I'll probably put it in the chat again once more when the presentation is over. But you can download this Unity project. And so in this clip circle shader, we've been doing all this stuff with textures, and that's all well and good, and we're going to keep this here. But something else that's interesting to consider is you can still use this position in this value. It's still possible to use this information here. Like for example, if we wanted to say we take the distance from the camera, for example, we could set that to be the color, and if we apply that to all of our shaders, we should get a really quite close to the camera kind of depth effect. So we see everything is white, but if I zoom in really nice and close to something, things that are right up on the camera will appear black. And we could, of course, scale this. And in fact, we will create a value that we'll need already. We can call it offset. And if we were to multiply this value like so, we can change this offset, and this on its own is even an interesting kind of effect. But this is ultimately not what we're trying to create. Just like last time, I'm going to create a vector 3 and call it pivot offset. This is very useful in a lot of circumstances to, instead of using the camera's position directly, to just give yourself the control of having a vector that you can use to offset the camera's position. And we'll hook that in. And we already have this offset. I'm actually going to rename this to a multiplier because we're multiplying. And we'll create another offset one because we're going to add an add node and hook this up. And this multiply and add pattern is something I use a lot. Really, it's a nice way to remap values conveniently. And if we attach that to base color, then we get yet another axis of control. We can push and pull, and the multiplier sort of changes the width of the band, and the offset controls how close it is to the camera. But this is an eclipse circle shader yet. So let's add this in here, and it's important. What I hope to teach with this shader is the fact that there's these nodes, but there's also more we have access to in the graph settings. And I'm going to quickly enable alpha clipping. So because this is the fragment shader, this runs for each pixel. And what the alpha clip threshold is it's a value that we can set for each pixel. And if we set this to greater than 1, the pixel will be discarded. And so if we see here, we've got everything, it's all well and good, because the alpha clip threshold is at 0.5. But if I set it to 1.5, which is above 1, everything disappears. That's not that interesting, though. Now, as we saw, that value that we had that showed the distance from the camera, if we add this to the alpha clip threshold, at first everything looks the same. Oh, and I just realized I should do this color thing as well. So we get the colors in the world. It was base color. Save that. Okay, we have our world color back now. And if we just tweak or we should select all the materials before we do this. If we tweak our multiplier and our offset, we find there's a circle around the camera. And just like last time, we can use the pivot offset to center it on the player. And we can make it tight, can make it large. We'll keep it relatively large for now. And this is an interesting enough effect. You could make an interesting video game with this. A cool way to limit the player's view. But ultimately, this is also a really nice way to teach the use of alpha clipping, which is a common technique often used, for example, to make, like the leaves on rendered trees, you can have a texture and use the alpha of the texture to clip pixels away from it. So instead of having to have a transparent texture, you can have a texture that is fully opaque in some areas and fully transparent in other areas. Yes, exactly, like for a horror game. It'd be really interesting to have a horror game with some kind of effect like this. And we'll see another use for alpha clipping in our next and final shader, a favorite of mine. And we'll call this. I usually think of this effect as like a shimmer, but you'll see that it's really quite adaptable. Actually, I made this off the wrong one. I'm going to duplicate our inflate shader for this. We'll call it shimmer, and I'm actually going to rename that so it doesn't sound like I'm yelling. And we will apply that to all of our materials in the scene quickly. Shimmer. And because we haven't modified it from the inflate, this is once again that inflate shader. And actually, I did forget that this is simply a character effect as well, so I'm even gonna set these all back to the defaults where they can remain for now. Nice and comfortable. And so if we open up that shimmer shader, we've got our texture, and that's cool. We should keep that. We have our inflate, and that should also remain. I'm gonna drag this just up and out of the way a little bit so we don't have to look at it too much. And we have our texture going in and our tint. I'm also gonna drag this up and out of the way a little bit. Because once again, we're mostly gonna be playing with alpha clip. Now, just like before, I need to enable alpha clip for this shader. And the core of this technique is using noise. In this case, I'm going to use gradient noise to do the alpha clipping. Just like the other clip, I'm going to create a clip multiplier and a clip offset. Two useful controls that serve almost any effect, multiply and offset. We'll set this up kind of back to front. Multiply and then add, and then we'll set this here, clip offset. And if we were just plug this noise in and take a look at our character, we might see some interesting stuff here. And the noise is quite big, so I'm actually going to also create a noise scale property that we can use to control how big our noise is. And by default, our noise is set scale as 0. And if we scale this up, this already gets us somewhere interesting. But we have all these seams everywhere from the character's UVs, and this is one of these situations where if I have all these controls over the world space, do I really need to use my character's UVs to position this? What if instead of using the UVs, I took the world space position? Or I'll actually use the object space position. And I split that out to get its different values. And I then use a vector 2 field to create our own custom UVs, perhaps. We'll plug in the x and the y value. And now we have this effect without any seams. There is one downside, though, which is that if we look at our character from the side, we can see it's quite stretched. And there is actually a way around to this. If we create, so this is essentially mapping noise onto the character on the XY plane. If we map noise onto the character on the XY plane and the XZ plane and the YZ plane, we can essentially use 3D noise. And so I'm going to create 3 noise maps, one for each character, or I'm sorry, one for each axis, and duplicate this out. And so that first one is on the XY. And so the second one I'll make the YZ, and for the final one I'll make it the XZ. And if I multiply these all together, just using 2 multiply nodes because multiply node only has 2 inputs, we should see a 3D noise effect. We have to tweak the effect a little bit. without seams or stretching. We just get the noise all over the character. And this already presents some interesting possibilities. Um, the reason that I included the inflate amount here is I could, for example, create a duplicate of my character's material, set the base material to the normal material, so he looks regular again, and then add our shimmer shader as a second shader on top of that one. Then, if I apply a slight inflate, more slight, more slight, there we go. Yeah, maybe just a little less slight. I could perhaps remove the texture, and now suddenly I have an interesting kind of effect here. I can change the scale of that. I'm not quite exactly sure what you'd use this specific effect for, but maybe if you wanted your character to be covered in paint or something like that, you could do this. And we see there's this interesting principle, or as the character moves around, it actually moves through the object space. And this is all cool, but we can make this cooler. There's a cooler way to set this up. And I think the first thing to make this cooler would be to animate it using the time node. So I'm going to add the time node. I'm also going to add an effect speed property, and I'll multiply that together. We have time multiplied by effect speed, and all I'm going to do is I'm going to add that to the position. So take my position here, go out, and I'm going to use this quick. I just did a nice shortcut you can use anytime if you double click on a line, you get a line node, which is very helpful for organizing your vector or your node graphs. Oops. And so if I connect this up here, we should see, if I've connected things right, increasing the effect speed cause the effect to animate over the character in a way that I find really quite lava lampish and quite interesting. But well, this sort of transformation of this effect is interesting. Where it is being applied, we are still essentially just seeing a color, and I think we could make this more interesting too. Um, and one of my favorite ways to make things more interesting is to apply an edge glow. So I'm gonna set up a quick edge glow for this. Oh, we need a color for that because all the best edge glows come in different colors. And we should have also a float to confirm or to control how powerful the effect is. How much of the surface has the glow effect applied to it. And I'll scooch all these nodes back to give us some room. And we're gonna need to we have our base color here, and instead of replacing this, I'm gonna temporarily disconnect it and we'll hijack it a little bit. And so if I take that edge glow material and if I were to connect this right to it, as you know, that allows us to control the color here. Now, I'm going to want to mix the edge glow and the tinted texture color, but I don't want to blend them per se. I more just want to smoothly transition between them. So I'm going to use a lerp node for that. Linear interpolation. And we'll connect those together and add that in. And now thinking about the kind of effect that we want. Right now, this will just have the same effect because all the lerp is set to 0. We want at the edges of this effect for we want a value of 0, and towards the center of the effect we want a value of 1. And what that essentially looks like is a distance from the edge of the effect. Now, if we remember from earlier, this alpha clip threshold, it clips away anything greater than 1. So we know the value coming in here is less than 1 anywhere it's solid and greater than 1 anywhere that it's transparent. And right at the edge, we know the value is 1. And this is a prime opportunity. Take a distance node and connect that value, and we can just set this value to 1. And so what this will give us is the distance from 1 at each pixel. And I can multiply this by the edge glow amount. And if we connect that, we should see something like the effect if we increase the edge glow amount. Oh, the edge glow amount set to the same color. And we'll set the color of this to white or even black. Now, this is kind of cool, but as you saw there, when I had this set to a color, like things can get a little weird. I'm seeing green values in here. We've got green, and really what we're seeing here is we're seeing colors outside of the normal realm. Uh, we've gone beyond where we should be, and that can create strange and undefined effects. It might look like this on my graphics card. It's not guaranteed to look the same on your graphics card. And so, while it looks cool, setting colors outside of the regular bounds of what colors should be is not recommended. Luckily, there's a handy node for this called saturate, which is essentially the same as a clamp function set to 0 or 1. I believe there is also a clamp. The clamp default settings in saturate are exactly the same, but saturate's one of those convenient functions that will really serve you your whole life long. And so if we apply that and we look here, now we can set the color to white and our edge glow. We can tweak that amount. And this is pretty cool, but it doesn't really look like an edge glow, does it? It kind of just looks like actually like we got a an edge red more than anything. And I'm also going to go ahead and just remove the base material so we only have our transparent character. We can even drop this palette back in. And so if we want this to actually glow, this is another property that we can set. If we look at the edge glow, we could set its mode to HDR. And I think this is one feature that might not be available in the built-in renderer, the HDR rendering. But if I save that, now this becomes an HDR color that allows us to control the intensity, so it can have emission. And if I go in here and I can make it really red and crank up the intensity, you can get this really quite enticing edge glow effect. And this is not necessarily an effect I would leave on all the time, but where I've really enjoyed using this effect before is for a death effect. And so this multiplier controls sort of how sharp the edges are, but we have this offset as well. And if the offset is sufficiently low, we won't see the effect at all. And as the offset goes up, we see the effect more and more until eventually the character disappears. So we have our lava boy, and we can change how much lava he has. And one of my favorite things to do with an effect like this is you start from -1 or lower just to make sure that there's no little blotches. And when your character dies, you can animate the clip offset so that they get this cool death animation and they vanish smoothly instead of just blinking out of existence. And with that, we can really you could really create an interesting looking fellow right here. And one of the things I love the most about shader development is how, in just a few minutes, with a few nodes, I've rendered the character we started with completely unrecognizable. We've strayed far from God. And with that, that brings us to the end of my planned demonstration. I'll real quick apply these to. I'll apply the Animal Crossing shader to the world, so I can run around a little bit with my my lava orb character. And if anyone has any questions, I'd love to answer them. If anyone has any clarification they'd like to see for any of the shaders that we've seen tonight, any questions about graphics cards,
While
now
we're
would be
waiting for folks to hop in with questions, I have a question for you.
yeah, absolutely.
Where did you learn the majority of this? Was it through watching other talks and workshops? Was it through like written documentation? Was it mostly through experimentation? Like, how did you end up learning a lot of this?
So um I had the advantage from the beginning of coming from a background of already knowing how to write shaders the old-fashioned way. So I got to skip a lot of the basics of learning how shaders work in general. Um, but from there, I definitely used, for example, Alan Zucconi's shader tutorials. Those are excellent. If you look up Unity shader graph and then anything, any kind of cool effect, there'll be someone who will have created a tutorial. I also, one of the things I love the most about the shader graph is unlike writing shaders in code, it is so much more forgiving in that it's much more, or it's much less prone to error out in a way that just makes your shader pink. Having to work with the nodes forces you to not forget a semicolon or anything like that. So there's so much more room for simply multiplying positions and vectors and changing the vertex position and tweaking the normals and doing a lot of fun, cool vector algebra to create your own effects and just kind
Yeah,
of see what you can make. It's so much more welcoming in terms of just being able to mess around like that.
heck
Um,
yeah.
and to answer this question here from chat, how do you apply shaders to the world? The way that I've done this is the world. I have all of the materials for the world right here. So I have, for example, um, this tree just happens to have the wood and leaves material that I have applied. If I create a new material, let's make it a default one, allow Unity to create that. And I go to some random tree, we'll do this one, and I apply this material to it. We'll see that if I go into the game and I run around, this tree doesn't have the shader applied to it. So as we run, it's a little hard to see because it blends into the sky. As we run along, it doesn't sync up with the world. It actually rises above. And this is one of the downsides of this. Uh, One of the downsides of this kind of effect is that you have to apply it to all of your materials. Um, in the case of something that controls the entire world like this, there's other ways. There are some ways around this, especially with the universal render pipeline. You could do custom passes and that type of thing that can get around this problem to some degree. But being able to apply something universally across many different shaders is definitely a more advanced topic. There's also the possibility of doing like a shader pass compilation. You can add custom effects to other shaders. That's something that even I have only dabbled in lightly. Yeah, it is flying away. The slowest rocket I've ever seen. Are the Lava Boy and Animal Crossing one on the player character at the same time? So actually, right at this time, we don't have the Animal Crossing shader on the player character, but because the Animal Crossing effect is oriented around the player character is already always in the right position. But if I was to, for example, make it such that the camera doesn't move anymore and run away with the character, just like the tree, because the Animal Crossing effect is not applied, we see that the character rises above the ground. But if I were to apply that Animal Crossing effect back onto this camera, or back onto this the player's material, the character will snap right back down onto the ground and be back in sync with the world. And so yeah, unless anyone else has any other questions, that's my presentation. And as I said before, I'll reiterate now the repository for this presentation. It's available on my GitHub. Send this here now, and as soon as this talk is over, I will make a commit and push all of the shaders I made during this. But as I said before, there's also sort of nicely organized versions of all of these shaders that you can copy and paste from or use as reference. And also, always feel free to tag me in the ROC Game Dev Discord if you have additional shader questions. I'm
I was
not
gonna say,
always incredibly good about keeping up with the chats, but I'm generally pretty good about replying to a tag promptly.
so two more questions that I've got. The first of which you mentioned it was easier for you to learn shader graph because you already knew how to write like old style shaders.
Mhm.
Um, you gave a talk on how to do shaders without shader graph a couple years ago, right?
Yes, I did actually. And that talk is still available and is still relevant to this day if you're interested in writing your own shaders, because there are some things that the shader graph can't do. Gasp. They're still developing it, still a work in progress, and there's still some techniques that you need to be able to write shaders for. Um, and I think actually, if you bear with me for 1 second, I have a link to um that talk. And I could send that in the chat as well if anyone happens to be curious to see that. Yeah, that's at bit.ly/shader workshop. And that's right here, bit.ly/shader workshop. That takes you to custom shaders in Unity, how to get started talk. And Sam, did you mention that you had one other question? No worries if not. Yeah,
Oh, sorry, I was on
you're
the
good.
wrong push to talk button. Do you have your Discord handle available to drop in case anyone wants to reach out to you there?
Oh, yeah. So I am just at Aidan Markham. I could put this in the Twitch chat, I guess is the best way to do this. Aidan
Yep.
Markham, hashtag 1360 is the number Discord has assigned to me as my sort of index. And yeah, if you were there, Patrick, you certainly would have seen some of these effects before, other than uh the new sort of shimmer effect that I created. The other three effects are based heavily on the effects that I did in my previous talk, because I still believe that those are quite good effects for teaching the basics. I think they cover, like, between those three, a really good percentage of the basic tools that you need to build more complicated effects.
Awesome. I think that's all I got for questions.
Awesome. Well,
Doesn't seem
yeah.
like we've got any more.
Thanks everyone for watching. It's always a pleasure to give a Rock Game Dev workshop. My third summer Rock Game Dev workshop in a row, 3 years in a row. I'm sure I'll be back in 2023 with some other interesting topic.
Thank you so much, Aidan.
Yeah, anytime.
And if you're looking to watch this again in the future or you want to send it to a friend, this should be live on our ROC Game Dev YouTube channel here in the archives within a couple days, usually. Um, and with that, I think that's it for the night. Thank you so much, everyone, for tuning in. Thank you again, Aidan, for a great talk. And we, the royal we, not me, we, but we will see you again in 2 months for the next talk. Have a great night, everyone.